Alright, and so that is done with the force V1, and you can immediately see these problems take up a lot of time. Okay? So I'm going to move this panel and see if I can maybe pull up the top one. You can all send a prayer on my behalf. Alright, can everybody see all the three panels? Okay, beautiful. This is heavy work. It's my workout for the day. Obviously, see, I need a workout. Alright, so we've accounted for the shear force. I want to talk about the bending stress before I go ahead and do the other ones. So perhaps what I'll do is, I will have this as a homework next week, not this week, you don't have a homework this week, maybe next week you can finish off the rest of this problem, okay? So with numbers added to it, so that you can use this as a template to get yourself started, okay? I want to talk about that bending moment M2, which is at an off axis. So the effect of M2, and I want to get rid of this pesky negative sign in this bending stress equation. Okay, because I want to understand how the bending process physically and intuitively takes place without recourse to sign conventions and so on. Alright. Okay, so here is my cross section. I'm going to draw my y-axis and the z-axis. This is the z-axis, okay? The directionality of the bending moment is given to me. It is pointing along the positive y-axis. Okay, so we're going to draw it out here. So it's directed along the positive y-axis, so this is M2. Which means for my M2 calculations, what is the neutral axis? First of all, what is the bending axis? The bending axis is the axis about which the moment is acting. And we said that the neutral axis is the same as the bending axis, so this is my neutral axis for this moment. It does not make a difference in a perfectly symmetric cross section. It makes a huge difference if you have asymmetric cross sections, which we are going to be looking at. Okay? So this is all teeing us off to that place. Next question to all of you. This is A. This is D, this is C, and this is B, and that was E. What is the value of the bending stress at the point A? Whenever I have a point on the neutral axis, there is no bending stress about that particular point due to the bending moment that is applied about that axis. Okay, so I don't have bending stresses due to the moment M2 about the point C, about the point D, and about the point A. So they are all zero. And I want to understand one more thing. Okay, so here is my cross section. My palm is my cross section. Imagine that there is a line that is running vertically through my palm, like my elbow is. And I am trying to see how the moment is applied. The moment is applied such that I take my palm and I push the left half of my palm into the board, and the right half of my palm comes out of the board. Can you all visualize this happening? Okay, so perhaps this might help us. I don't know. Maybe not. But okay, so here this is the plane. Okay. So the way the bending moment is applied is I'm taking the screen and I am rotating it this way, which means that all the fibers here are getting pulled out, all the fibers here are getting pushed in, which means that I immediately know, without recourse to this pesky negative sign, as to what part of the cross section is tensile stress and what part is compressive stress. Does this make sense to everybody? Question, 2 hands, okay, first time.
So in the cross section here, are we saying that the right side is getting pushed in and the left side is getting pushed up?
Right, okay, so this side is getting pushed in,
Okay.
and this side is getting pulled out.
Okay.
Right. Yes, sir. Right. So the bending moment is trying to take all these fibers. So if you imagine like long lines of fibers, they're just getting pushed inside. Okay, so this part is going to be in compression. All of this. All of these tension. Okay, and while I'm at it, let me also draw the other cross section. Okay, so effect of M1. Draw the same thing. Okay, so in this situation, my y-axis is pointing vertically, same axis as before. Okay, the axis is really important. It's not like these axes have to be y, z, and x all the time the way I've drawn it. You can change the perspective of the axis. But the subscripts will tell me, okay, what is the directionality of these stresses. So moment is applied. Let's say M1. Now if this is the case, then I'm just going to take this as my example one more time. Okay, so I'll wait until all of us are done. This is the cross section. The way the moment is acting, if you assume that my hand here is the positive z direction, what's the neutral axis for this bending moment? It is the z axis, right? Because it is the bending axis. So this is the neutral axis. The first point of interest that I have is that at any point along the neutral axis, the bending stress is 0. Okay, so at all points along the neutral axis, zero bending stress. Okay, so where are the things? Where are the points where things are 0? For the bending stress, all points along the neutral axis. For the shear stress, at all points along the neutral axis, the transverse shear stress is a maximum. Please never forget these two statements. Okay, the neutral axis is why, this is why it is a special axis. This is why you studied centroids in statics, and this is why you are studying moments of inertia in statics as well, so that you can use them to calculate the stresses. And one of the things that you do in manufacturing is you want to optimize this moment of inertia. Okay, you want to come up with a cross section that is the most optimum in terms of design, something that is lightweight, very efficient, which does not take up a lot of space, which does not take up a lot of material. And so all of these stress calculations will go into that, the design considerations. Okay. If you're taking machine design or machine elements, you come across these next semester. Alright, so if I look at this guy, here is the example. My arm here outstretched is the z-axis. The moment is acting such that if I curl my fingers, my thumb is pointed along my left arm here. So I'm going to take this guy and rotate it this way. So this was originally straight. I take the screen, rotate it, so which means that all the fibers that are on the top are getting pulled out. All the fibers that are on the bottom half are getting pushed in. Once again, this is the cross section in front of you, this is my neutral axis. The moment is applied such that if I do it this way, all these fibers are getting pulled towards you, these fibers are going away from you. They're getting pushed into the cross section. Okay, so this is going to be in tension. And so it is now easy to calculate. I mean, if I look at the bending moment M2, all of these points are 0, so the bending moment at E and B due to M2. Okay, so sigma at E due to M2, I can outright find out that this direction is going to be along which axis? The direction of the bending stress at the point E is going to be along the direction of the bending stress. So, which directions are the fibers getting pulled or pushed? They are getting pulled or pushed along the x-axis. Right? So, which means that the subscript is going to be the same here, the normal is also the x-axis. So, always remember, if you are doubting the direction of the bending stress, just put the second index, which is the area normal. The first index has to be the same as the second index, only for bending stress. Okay? So, this is just M2 times y, which is just going to be all the way from here to there, which is r. Okay, so this is M2 times r. Y, the moment of inertia, pi by 4, r to the power 4. Okay, so this is going to be in a state of tension. So typically, if you have a tensile bending stress, you write it as a positive sign. Then sigma B due to M2 is going to be compressive but at the same value. So minus M2 or by 4 or to the power 4. And this is also along the x-axis direction. And at any other point, the bending stress is 0. So all of these points, 0 bending stress. And likewise, so this is C, this is A, this is D, E, and B. Sigma at the point A and at the point D will be the same magnitude except the moment will be M1, but all the other points, the bending stress will be 0 due to M1. Okay, so these guys here, the bending stress will be 0 due to the moment M1. So I can write this as sigma at E, M1 is 0, sigma at C, due to M1 is 0. So the centroid never feels any bending stress. That's also a special point. Sorry if this kind of blocks people's views here. The centroid does not feel any bending stress. The only way to make a centroid feel anything is by applying a normal force. Either going to pull it or push it equally, like an average normal force. And likewise here, I could have said that sigma at point A is 0, at C is 0, and at D is 0. Tensile, compressive. So sigma A due to M1, once again in the XX direction, because the area normal is X, I know what the second index for the bending stress is. I know automatically I know the first index. It has to be the same. This is going to be tensile, so plus M1 by Y. Y is the distance from the neutral axis all the way to the point A. Divided by pi by 4 r to the power 4. Likewise at D, it is going to be compressive. Minus pi by 4 r to the power 4. Alright, does all this make sense? Can you visualize all these things? It's a lot to keep in mind, which is why you've got to tackle this problem piecemeal by piecemeal. And what we will be seeing in the coming lectures, I'm going to start putting numbers to many of these things. We'll draw shear force bending moment diagrams quickly. Then we will realize, okay, here are the sections where the moment and the shear force is the maximum. Then we will start doing these calculations at exclusive points on the cross section. And most importantly, this will not be our cross section from now on, it will be something a little more complex. And to help us with that, I am going to post some review notes on moments of inertia from basic statics. Parallel axis theorem, you might recall parallel axis theorem. So we will make use of those concepts again. Okay? Thank you for your patience and good luck in the exam.
Yeah, I probably saw it. I was like trying to go like this. I was going like
There's
this.
only the three of you. And then everyone's staring at you. It's like,
Scared, man. Every time I want to do it, I'm like, oh, but this is gonna get pushed in. I'm just pushing it in.
science shit.
I'm ready to get super confused.
Right.
Yeah, because we have a quiz.
Oh, I thought you were on camera.